So in this video lesson, we're going to have a look at the different types of forces. So this is the beginning of our forces unit. And so forces can be thought of as either a push or a pull on an object. So if you are pushing an object either left to right, up and down, or we're pulling an object either left to right or up and down, or it doesn't have to be you that is pushing or pulling, but it could be a force that's acting in the environment that is doing this push or pull. Since it's a push or a pull, it must have direction, which means that our forces are vectors. So they have both magnitude and direction. So every time we're dealing with a force, we have to talk about the magnitude of the force, but also the direction that the force is going in. So the symbol for forces is a capital F, and we're going to have that arrow over top because it is a vector. So we know that vectors include both magnitude and direction, and so our force has the little arrow that signifies that it is a vector quantity. So there are two different categories of forces. So we have fundamental forces, and then we have engineering forces. We are going to focus more on engineering forces than fundamental forces, but I'm just going to talk about the different kinds of fundamental forces there are. There's 4 different types, and so the first one is gravitational. Which we will look at a little bit. And then we also have electromagnetic. And then there is the strong nuclear force and the weak nuclear force. So the gravitational force we're going to talk about in a little bit more detail. Gravitational force is going to happen between 2 large objects in the universe. Electromagnetic we will talk more about when we get to electricity and magnetism in terms of that unit. And then the strong and weak nuclear forces we're going to spend very little time on because you're going to spend a lot more time on that when you get into more advanced physics. Strong nuclear force and weak nuclear force are the forces that are keeping atoms together. So they're actually what holds like the nucleus of our atom and the electrons traveling around. It's what holds the atom together. All right. So then our engineering forces, which we're going to spend much greater time on in this unit. So some different engineering forces are the gravity force. So you may have heard of gravity before. The normal force, and we're going to talk about what that means. A tension force. A force of friction. Or an applied force. So we are going to go through each of these forces just to explain a little bit more about them. And so we're going to start with the only fundamental force that we're really going to look at. And so we're going to start with this gravitational force. Okay. Again, electromagnetic force. Electromagnetic force we're going to get to a little bit more when we deal with electricity and magnetism. Strong nuclear and weak nuclear forces. Again, those are what are holding atoms together. And those we're not going to focus on. So we're only going to look at gravitational as our large fundamental force, and then we'll look at each of those engineering forces. So when we look at the gravitational force, so a gravitational force is an attractive force between 2 objects in the universe. Okay. With the gravitational force, It has to be between two objects. It is attractive, so they are wanting to be close together. and it can be any two objects in the universe. It does not matter how heavy they are in terms of their mass. It doesn't matter how light or how heavy. It is a relatively weak force in terms of the fundamental forces. So electromagnetic and strong nuclear, weak nuclear forces are quite a bit stronger than the gravitational force. But the gravitational force is still a strong force. It's just not as strong as the other fundamental forces. Okay. So then when we look at our engineering forces, so when we are dealing, I forgot to give you the symbol for gravitational force. So the symbol for gravitational force, we're using F to represent our force, and gravitational force is F with a capital G. It is extremely important that you use a capital G here for gravitational force, because gravity force, which is an engineering force, is going to have a different notation, but they both start with a G. And so you have to be really careful here. You want to make sure gravitational force is capital G. Okay, so then when we look at our engineering forces, and we're going to start with our gravity force. Our gravity force is going to be noted by our F, of course, and a little g. Okay, and the gravity force is the force between doesn't want to let me write force today. So the force between a huge object, and by huge I mean the size of a planet. So like the Earth, and a small object on its surface, or close to the surface. Okay, so when we're looking at gravity force, a gravity force is that attraction between this huge planet-sized object like the Earth and a small object like a person or a building or a basketball or an airplane. Something that is small in comparison to the size of the planet and is either on the surface or is really close to the surface. So even an airplane would work here, because even though the airplane is not necessarily on the surface all the time, it is relatively close to the surface, okay? Meaning that it's still within reasonable distance from the Earth, okay? It's not really outside of the Earth's atmosphere. We're still in the atmosphere when we're flying in an airplane. And so we're gonna be dealing with gravity force there. All right, next up is our normal force. All right, so a normal force, we use an F with a capital N to denote our normal force. And this is the force a surface pushes with when it is pushed on by an external force. All right, so a good example here is if we were to lay a textbook on a table, okay, a normal force is the amount of force that the table, which is the surface, will push up onto the textbook, which is the object that is pushing down on the table, okay? In order for us to have a normal force, one of the most important parts is that we need to be dealing with a surface. We have to have objects that are in contact with each other okay? And so we are going to do some examples with that about when there's a normal force and when there isn't a normal force once we get into drawing some diagrams. All right, next up is our tension force. And with our tension force, switch to blue here. We can denote it with, again, a capital F with our capital T, or you will see often that tension is just denoted with a large capital T with the arrow over top. Okay, this is the force on an object that has been, there's a couple of examples here, stretched, compressed, or twisted. Really, to have a tension force, we need to be dealing with ropes or strings or cables or springs. Really anything that can be compressed or stretched or twisted. So if you think about a rope or a cable, so a cable that is, say, on a crane, something like that, so any of those types of cables, or something that's on a string, or something that is in a spring. So if you think about like a slinky would be a great example of a spring, something that can be stretched or compressed or twisted. And so that's when we're going to have tension forces. Okay. Next up is our friction force. And so our friction force is denoted by, again, a capital F, and we're going to use a little f in there, okay? And this is the force with which a surface resists the motion of an object moving along it. Okay, friction force, I'm sure you could think of an example like tires on gravel, or tires on the road, or tires on snow, okay? And so anytime we have two objects that are moving, so an object that's moving on a surface, any two objects that are moving against each other or rubbing against each other, they're going to have some type of friction force, okay? All right, and then the last of our engineering forces is our applied force. Okay, and so our applied force is usually denoted with FAPP for applied, okay? But sometimes applied force isn't always named applied force. So sometimes you can say pushing, or so an applied force is a force where an external factor changes the state of the system. Okay. For applied force, we're going to actually draw two examples here, just to show the difference between what is an applied force versus what is not an applied force. Because applied forces actually require contact with the object. So we're just gonna draw a desk here. And on my desk, I'm going to put a textbook. And so I'm just gonna draw the same system twice, and I'm gonna show you when it would be an applied force and when it would not be an applied force. Okay, so I'm gonna draw someone pushing the textbook. So this is just someone who is pushing a textbook across a desk, okay? All right, and then same thing here. So we have a person who is pushing a textbook across a desk. Now, the difference between these two. So my one on the left is going to have an applied force, and the one on the right is going to have no applied force. So the one on the left has an applied force because the person's hand is continually pushing on the textbook. There is always contact between the hand and the textbook. So the person is pushing the textbook across a table, but the person's hand is in constant contact with the textbook. On the right side, there would be no applied force in this example because the person pushes the text then removes their hand, so there's no contact. And the textbook is just sliding across the desk. Okay, so I'm sure all of you have done this at some point on your desk, at one of the lab benches at school, on the kitchen table at home, okay, or at a table at a restaurant. Like, I'm sure this has happened to every single person. Either you push something across the desk without continually placing your hand on it. So you give it a little shove and it slides across the desk. That would be no applied force. Or you are shoving it across the table, but your hand is in continual contact with the object. That would be an applied force, okay? So if you want to ask yourself whether there's an applied force or not, you always want to know, do you have continual contact with the object? If there is no continual contact, there is no applied force, even if you gave it a push, okay? You have to be pushing continuously on the object for it to be an applied force. All right, so we are going to look very specifically into gravitational force, okay? And so that's just our different types of forces, and we are going to look specifically at doing some calculations for gravitational forces. Okay, so gravitational forces, we remember, is F with the capital G, and it is the force between two objects in the universe, okay? Gravitational force is also called Newton's law of universal gravitation, okay? And I'm going to give you the mathematical formula, and then we're going to dissect the mathematical formula a little bit. So here's what the mathematical formula looks like. It is a capital G. There is M1 multiplied by M2. And then that is divided by D squared. Okay, so we are going to talk about each of the parts of this formula. So Fg is gravitational force. Again, please do not forget that gravitational force is between two objects in the universe, okay? And so it's just between two two objects within the universe, and is not the same as gravity force. Okay, so please make sure you know the difference between those two. All right, capital G is actually a constant and is called the gravitational constant. It has a value of 6.67 times 10 to the negative 11. It's extremely small, but it is constant in our universe. So as long as we are dealing with objects that are in our universe, this is our gravitational constant. If we were to, say, go to a different universe, the gravitational constant would likely be different, theoretically anyways. Okay, M1 is going to be the mass of object 1. M2 will be the mass of object 2. And then D is going to be the distance between them. Now, really important here, this is center to center distance. Okay, so we are going to draw a case where this would be true. So we are going to draw a picture here. This is going to be the Earth. And then over here, we're going to draw the moon. Okay, so we are looking at finding the gravitational force between the Earth and the moon. And so the gravitational force is what's actually keeping the moon rotating or revolving around the Earth rather than just floating off into space. Okay, and so between the Earth and the moon, we have a gravitational force that is an attractive force. So it is attracting the moon and the Earth to each other. Okay, so we need some object information about the Earth and the moon. In order for us to calculate that gravitational force between the Earth and the moon, we have to use our gravitational constant. We need to know the mass of object 1. So we'll say that the Earth is object 1. And then the mass of object 2. So we'll say the moon is object 2. And then we need to know the distance between them from the center to the center. All right. So first thing we're going to say is that the mass of the Earth, this is actually a constant value. So it's 5.98 times 10 to the 24 kilograms. Okay. This constant, as well as our gravitational constant, are actually in the bottom of your formula sheets. I would never ask you to memorize the mass of the Earth or the moon, okay, or any other planets in our solar system, nor would I ask you to memorize the distance between them, okay? Those would always be given values. If they're not given in a practice question, you can always look them up, right? They're relatively standard values. So then we're going to have the mass of the moon, and the mass of the moon is 7.35 times 10 to the 22 kilograms. We want to make sure that our masses are going to be in kilograms because that is a standard unit for mass. And so we want to make sure that we're using our masses in kilograms, which is not hard since these are very large objects. All right, now the distance between the Earth and the moon is also a known value. And so there are 384,000 kilometers from the surface of the Earth to the surface of the moon. But what I want you to pay attention to is that for that distance, to calculate that gravitational force, we need to know the center to center distance, okay? Which means we also need the radius of the Earth and the radius of the moon. So we're gonna add those in there. So the radius of the Earth is 6,400 kilometers. And the radius of the moon is 1,735 kilometers, okay? So then in order to get the distance from the center to the center, we're gonna add up r2 radius as well as our distance from the surface to the surface. Okay, so let's just do that right now. So distance is going to be our 384,000 kilometers plus our 6,400 kilometers plus our 1,735 kilometers. So we're just going to do that math here. So we're dealing with 392,135 kilometers, okay? Now, the other problem is that kilometers is not our standard unit for distance, and so we're going to turn that right now into meters. So we're just going to multiply it by 1,000. So we're going to get 392, 135,000 meters, okay, because we want to have our distance in meters. So now we have everything that we need to plug into our formula. So we have our mass number 1, we have our mass number 2, we have our distance, and we already know our gravitational constant. Okay, so the gravitational force between the Earth and the Moon, we're going to go our gravitational constant, 6.67 times 10 to the negative 11. Mass 1 we said was the Earth, 5.98 times 10 to the 24. It doesn't matter which object you pick as object 1 and object 2. It will make no difference since we're multiplying. The mass of the Moon, 7.35 times 10 to the 22. Both our masses are in kilograms. Our distance on the bottom, 392,135,000, and that's going to need to be squared. Okay, again, you want to make sure masses are in kilograms, distances are in meters. And so then we're just going to plug that into our calculator. You want to get really comfortable with brackets on your calculator. So I'm just plugging this into my calculator right now. And I'm getting a value of 1.91 times 10 to the 20. Okay, and forces are actually measured in the unit newtons. Okay, so the unit for force is the Newton. So it's a capital N. Okay, and the main reason for that is because Isaac Newton is really one of the inventors of, not inventors of forces. He didn't invent the forces, but he did do most of his research in uncovering and developing what forces actually are. And so one of his most famous ones is supposedly that while he was actually in quarantine, during the plague in the 16th century, 1600s, give or take, in England, and he developed the idea of the force of gravity because an apple fell on his head when he was out underneath his apple tree. I don't know how accurate that is in terms of historical accuracy, but that is supposed to be the story, that the apple fell on his head, and Newton did a lot of research into the force of gravity. All right, so those are our gravitational forces. Now I do want to talk about the actual force of gravity. So you guys are going to do some more practice with those gravitational forces, with doing calculations with gravitational forces. But I actually want to talk about the force of gravity as well. And so the force of gravity is one of those engineering forces, and it is the F little g, okay? And so the difference between the two is that gravitational force is between two objects within the universe. The force of gravity is between a very large object, okay, and something that is either on or near the surface of the Earth, or of the object, we use it in the Earth, okay? And so what actually happens is that we use the gravitational force equation to actually come up with the force of gravity, okay? So what we do is we know that the gravitational force equation is G, and if we were on the Earth, it would be the mass of the Earth times the mass of our object divided by the radius of the Earth squared. Because if the object is either on or near the surface of the Earth within 100 kilometers, then the distance at the bottom of that equation is going to be the radius of the Earth. So what happens is that all of this section ends up being a constant value because those values never change. The mass of the Earth stays constant. The radius of the Earth is not going to change. Neither is our gravitational constant. So we end up with a gravitational force that ends up being the mass of our object times a constant. And so we actually named this constant little g, okay? And we call it the force of gravity on the Earth, okay? And so this ends up being our constant. And it happens to be 9.8. Okay, and so what happens is that in order to calculate the force of gravity, we're going to do the mass of whatever object we have times g. And so that's how we came up with this formula for the force of gravity. It's based on the gravitational force, but the force of gravity equation we can only use if we are on or near the surface of the Earth. If we are in space, then we have to use gravitational force, okay, versus force of gravity. And I know they sound very similar, so you have to be really careful with whether you're talking about gravitational force or whether you're talking about the force of gravity, okay? And so when we are on or near the surface of the Earth, Fg equals mg. This formula is not on a formula sheet. It is the most important formula in physics. Okay, it is absolutely the most important formula in physics. We are going to use it significantly all the time. And so Fg equals mg, you need to memorize this formula. Okay, most formulas are going to be given on your formula sheet. Fg equals mg is not on your formula sheet. You need to know this formula. Okay, now we can also call this something else. And the force of gravity can actually also be called weight, okay? So you might have heard this before. When you go to space, astronauts are weightless. That doesn't mean they don't have mass. It means they don't have weight, okay? And so there is a very large misconception between mass versus weight. So mass is actually measured in kilograms and weight is measured in newtons. It's a force, okay? Mass is how much stuff you're made up of, okay? And weight is how the gravity of the Earth affects you. Okay, so when astronauts go to space or to the moon, okay, their mass stays the same. So an astronaut here on Earth has the same mass as an astronaut on the moon, as long as it's the same astronaut. They'll have the same mass, but their weight will be different. Okay, if you're in the International Space Station, I'm sure maybe you've heard that when you're floating in the International Space Station, astronauts are weightless. And that's true because the force of gravity on the Earth is not affecting them. They are far enough away that the gravity of the Earth is not actually affecting astronauts. If they go to the moon, okay, astronauts on the moon are not actually weightless because the moon actually has gravity that is acting on an astronaut as well. It doesn't have the same amount of gravity as the Earth, though. And so if you've seen video of, for instance, like Neil Armstrong bouncing on the moon, That's because the moon still has some gravity, but not the same amount. And all that's different is that that value for G, that constant, is different on the moon than it is on the Earth. Okay, and so it has a different effect on objects. Okay, all right. So this is the end of our video lesson on the different types of forces. And there is some practice for gravitational force that you're going to want to complete after this lesson.